The first speaker is Jonathan Paley from Fermilab, and he is a member of NOVA collaboration, and he is going to tell us about accelerator-based neutrino beams. So John, over to you.
Okay, all right, well, thank you. And my apologies for not being able to be there in person. But even though I'm not there in person, since this is a school, you know, I want to provide you all opportunities to interact with me as much as possible. So throughout my slides over the next 3 lectures, I have some questions in my slides that I would love for you to answer. And then I'd also like to ask everyone to please send me at least one follow-up question after each lecture. I'll answer at least one question from each of you, and I'll post them in Slack. And I've created a flux and cross-section experiment channel there. So you can send me questions either via email, my email is there, or on the Slack for the school. Okay, so with no further ado, so a quick outline of today. Whoops, sorry, I have another thing that's popping up, getting in my way. There we go. Okay, so today I'm going to talk about neutrino beams, accelerator-based neutrino beams, and so I'll get into the why and how we make them. Then I'll talk a bit about neutrino flux uncertainties, their main sources being hadron production and beam focusing. And then I'll talk about how we go about constraining the flux and the uncertainties with both in situ measurements and ex situ measurements. And then I'll wrap it up with a look to the future. Okay, so why do we need neutrino beams? Well, you know, we are trying to understand the neutrino, so we need to do measurements with neutrinos, so we need a neutrino source. Nature is kind and provides lots of sources of neutrinos across many orders of magnitude of energy, and also reactors are a great source too, right? So we have neutrinos from the Big Bang, neutrinos from supernovae, neutrinos from the sun, atmospheric neutrinos, reactor neutrinos, and yes, sometimes people like to say even bananas give us neutrinos, but in fact, Swiss chard is a vegetable, is a leafy, a very tasty leafy vegetable that has actually a lot more potassium than bananas. It's, I think, the vegetable that has the most potassium. Okay. So one question for you all is, what are some other sources of neutrinos that nature provides us? Okay, so so it's nice, nature gives us lots of neutrinos, they're all around us, but we can't really control what we get. And if we want to do an experiment, we like to have control over our source. And beams offer control over neutrino energies, both and direction and time. Now, it's relatively easy, and I'll get into, the ways that it's maybe not so easy, but it is relatively easy to produce GeV scale energy beams of neutrinos on Earth. And as it turns out, these are great for studying neutrino oscillations and neutrino scattering, both of which offer possibilities for the discovery of physics beyond the standard model. And so the PM&S matrix shown here that you learned about last week, it can be broken down into 3 components and for convenience. And you can see that for atmospheric and accelerator neutrinos, as we have access through muon neutrino disappearance and electron neutrino appearance with starting with a muon neutrino, that we have access to several of the parameters of neutrino oscillations, right? And the way we do this is by starting out with a beam of muon neutrinos and looking for either their disappearance or their appearance into electron neutrinos. And if you look at the energies that are of interest for us, as it turns out, GeV energies are kind of the scale that we're dealing with. Okay. Now, how do we make a neutrino beam? So the basic principle is pretty simple. All we do is we take high energy protons from an accelerator, we smash them into a target, and the target is typically made out of graphite or beryllium. And when we do that, we create showers of hadrons, including pions and kaons. Those pions and kaons come out of the target, and they eventually decay and leave muons and neutrinos. And then the muons are absorbed in typically rock, leaving basically just a beam of neutrinos for us to use it for our experiments, right? So pretty straightforward. And in fact, the very first beam of neutrinos for an experiment was created at Brookhaven in 1962, where they took a 15 GeV proton beam, they struck a beryllium target, and that produced secondary hadrons. These were mostly pions. The pions decay to neutrinos and muons. The muons are stopped in an absorber, and then the neutrinos go on and interact in their detector, which at the time was a spark chamber, to produce electrons or muons. So this particular experiment is pretty famous. It was done by Leon Lederman, Melvin Schwartz, and Jack Steinberger, for which they won the Nobel Prize because it led to the discovery of the muon neutrino. Okay, so if we go back into our recipe, so that that was a long time ago. That was over 60 years ago. But modern day beams function pretty much on the same principle, but we've made some improvements over the years. So first, we use magnetic focusing horns to increase the overall flux by about a factor of 6. And then we can also use these horns because they are focusing either they either focus positive particles or negative particles. And when they focus one, that means they defocus the other. And so you end up with a beam that is basically 95% pure neutrinos or antineutrinos. And so basically you end up with a beam of just neutrinos or antineutrinos, right? So, one question is, why would that be useful? And then we also typically have a long decay pipe to allow more hadrons to decay. And that decay pipe is often filled with helium, right? Now, why would we fill the decay pipe with helium? Think about that and let me know what you think. Okay, now, I mentioned that we slam these high energy protons into a piece of material, a target, and these targets are often pretty special design. They are typically long, meaning that they have about something like 2 interaction lengths, and that's in order they're long so that we maximize the production of pions because that's where the neutrinos come from. The targets, though, are thin, right? So radially, they're not very large, and sometimes they're segmented, meaning there's gaps between, like air gaps along the length of the target, and that is because we want to make it easier for the pions to escape. So once we produce a pion, we don't want them going through even more material because if they do go through more material, they're likely to scatter or interact, and then we lose the pion, right? So they're long, but they're thin, so that we can get as many pions coming out. And then there are many other considerations, very just practical considerations for the targets in terms of the material and the design. These days, we put a lot of protons, we inject a lot of protons into these targets, and so they get very, very hot temperature-wise, so they have to be able to handle high thermal conductivity, and we have to make sure that the material has a melting point well above the operating temperature. We also have to make sure they're mechanically stable. All of these things that go into consideration when we're designing a target for an accelerator-based neutrino beam. Now, the focusing horns, the concept of the magnetic focusing horn was developed in 1961 by Vandermeer. So the idea is, essentially, you have a parabolic cone, and the current flows along the length of a cone, producing a toroidal field that focuses positive particles and defocuses the opposite sign, right? So if you want positive particles, that means it defocuses the negative particles. You can flip the current and get the opposite, right? So this results in a large increase in the neutrino flux, as well as a neutrino beam. And purity is critical for CP violation searches and hopefully measurements in the future. So I'd like you to think about that. Why is purity so important for CP violation searches? These days, we use multiple horns in our beam lines because by adding additional horns, you can capture mesons that are either under-focused or over-focused. So, for example, NUMI, it consists of 2 horns, and the LBNF, the future LBNF beam, and the TDK beam have 3 horns. So this is a way to kind of correct for over focusing or under focusing. And then you have to put all of this together, right? So you have these sophisticated, complicated targets, and then you have these really amazingly sophisticated horns. These are just some pictures of what they look like, right? These are just mechanical designs, but you can see all of these components that are in there. Sometimes we use water to cool everything to keep the temperature stable. And so these are very, very complicated systems that require years of engineering and R&D. And so there, you can see from the pictures just how complicated they are. The target is often put inside or at least very, very close to the first focusing horn. Again, that's to maximize the acceptance of the pions, meaning you get more pions that undergo the focusing effect. And then careful consideration is needed for the support structure and the remote handling for these, for removal and replacement of all of the elements. So we're exposing these to enormous amounts of a proton beam. All of these components become radioactive. And so, we can't just send a person in to go fix something. We often rely on robotic arms and other systems to adjust the components on all of these systems. Okay, so now I want to talk about neutrino flux predictions and uncertainties. And I'm sorry I can't, I can't see the audience right now. If there are questions, feel free to interrupt me. Okay, so here's a look at what the actual fluxes look like for some of our modern day experiments. And you can see it runs, about an order of magnitude across in energy. And the neutrino beams are typically designed for the baseline, right? So last week you learned a bit about oscillations, neutrino oscillations, and you learned about the L over E term. And so, typically we fix L, right? We decide where we're going to put our FAR detector. And then once we know L, then we know the energy that we need. And so then we design our beam for the energy. So for example, T to K and hyper K, the baseline is about 250 kilometers. And so the energy peaks around 600 MeV. Nova and Dune have baselines that are of order 1,000 kilometers. And so their energies are, on the order of 2 to 3 or 4 GeV. Now, for the SBN, the short baseline neutrino program at Fermilab, this one is actually also a very short baseline. And so the energy, but in this case, the energy is quite low, right? So the question is, why is the SBN peak so low, given that we're talking about less than a kilometer of of a baseline for the SBN program. And then finally, just to note that the Dighe and NOVA experiments both have their detectors off axis. And so there's another question is why would we move off axis for these experiments? Okay. So what we are trying to do in our experiments is to basically observe the either disappearance or the appearance of a different kind of neutrino in our FAR detector. And so effectively what we're doing is we are measuring the energy spectrum in our of neutrinos in our detectors, right? So the number of events that we observe at a given neutrino energy is basically your flux times your cross section, and then you have an efficiency, and then the probability that your flux or that your neutrinos have oscillated. So that's that entire product, and then you have to then apply a smearing of your true energy to your reconstructed energy. So in an ideal experiment, the flux cross-section inefficiencies of the near and far detectors would simply cancel, right? So you have these two, you would have this term for the near detector, you'd have the same term for the far detector. In the near detector, the probability that things have oscillated is basically zero. So it's effectively, that term is one.
Excuse me, John,
Yeah.
I'm just curious if you can move the cursor around to show like which line you are talking. If it is not a big problem, yeah.
It's not showing my cursor for some reason.
It's not showing your cursor. Okay, then it's fine. Yeah, now I can see the cursor. But somehow it doesn't, yeah.
Yeah, so I'll tell you what, I will highlight what I'm saying here so that you can follow along. Okay. So again, so in an ideal experiment, right, you have this entire equation, you have this for both your near and then your far detector. And you basically want to take the ratio, right? Because in the near detector, this term is 1. And then you take the ratio, right? So the ratio of these, of the far detector to the near detector would give you your probability as a function of neutrino energy. And in an ideal experiment, the flux and the cross-section and the efficiency would simply cancel, right? They're all identical and they would just cancel. But in reality, the near detector typically sees the near detector typically sees a line source. And so if this is the near detector down here, right, you can see that it sees kind of the entire spectrum of neutrinos in this kind of cone here, right? But at the far detector, the cone is so large by the time you get out here that this basically just sees the neutrinos as coming from a single point, okay? And so the fluxes are actually not the same. Even in the absence of oscillations, if there are no oscillations, the fluxes would look different, right? Because you have neutrinos of different angles and different energies here than you do out here. Okay, so now for the last bullet here, the acceptance and performance of the near detector is often different from the far detector, right? The far detector is typically this huge thing. The near detector is you know, we make it smaller because we can, because the far detector is very expensive. And so that means that the acceptance of the near detector and the performance of the near detector is going to be different. And so the efficiencies are different, and they typically depend on neutrino energy. And the efficiency corrections rely on a reliable flux model. All right, so I'll talk a little bit more tomorrow about how cross sections come into play here as well. But the flux, because the flux is basically the number of neutrinos as a function of energy. If you're going to make an efficiency correction, you need to know how many neutrinos there are at a given energy. Okay. Now, Now, if we look at other measurements, perhaps maybe not the three flavor measurements that we do in oscillation experiments, but instead we look at maybe measurements that we're doing in a single detector, then flux is a limiting systematic for all neutrino cross-section measurements by the current experiments. At least that certainly was true up until the last couple of years, but it is a very large uncertainty, certainly in the beginning of an experiment. Now, so there's a global effort to measure neutrino cross sections because, as I will talk about tomorrow, they are very important for the oscillation physics. And so there are a lot of experiments out there trying to make measurements of cross sections, but the largest uncertainty, kind of on the order of 10%, comes from the flux. And so we want to use the current measurements to tune our neutrino scattering models. And again, I'll talk about this in the next two lectures. Because the uncertainties in these models impact the sensitivity of the future Dune physics program. And so if you have a 10% uncertainty on the flux, that basically means you have a 10% uncertainty on the cross section. Okay, and so that's a very large uncertainty. Now, also, if you're trying to make other measurements, perhaps with a single detector measurement, or you can't rely on the three flavor oscillations to kind of cancel out between near and far. So, for example, if you're looking for sterile neutrinos, then that means you can't really use your near detector to constrain as well, at least. You can't use it to as well to constrain the flux and cross-section uncertainties as you can in the three flavor, because you now have an extra some extra degrees of freedom. And so as you can see in the plots on the top, if you ignore systematic uncertainties, but then you include the beam uncertainties, that's that orange line here, then suddenly you get a very large drop in your sensitivity, right? In your for the sterile angles. But also, if you want to, let's say, look for new physics, then you need to understand your flux. If you're looking for new physics in your near detector, then you need to be able to say unequivocally that some excess that you're seeing is not because of the flux, right? So any new neutrino physics, NSI, neutrino magnetic moments, etc., these will be limited to a certain extent by flux uncertainties. Okay, well, so that's going to be a problem. So why don't we just go out and measure the flux? Well, it's easier said than done. So first of all, we don't know the energy of the incident neutrino interactions. We have to infer it by reconstructing the energy. And even with our best detectors, for example, liquid argon time projection chambers, this introduces some model dependence. Now, also, since we observe, the number of events we observe is effectively the flux times the cross-section in our detectors. I'm on the third bullet here. We must rely on cross-sections that are already well known to extract the flux. By far, the best candidate for this is neutrino electron scattering, but this is a very rare process. It's about 1,000 times smaller than that of the charge current interaction. And it can really only be measured well for energies in the GeV region. It takes time because this is such a rare process, and sometimes it takes years to collect and analyze the data. And now, that said, it provides a constraint on the total rate. It mostly is a constraint on the total rate, the total flux, but it can also, in some cases, provide limited constraints on the shape of the flux. It is important to have strong a priori constraints on the flux when we first turn on the beam. right? So we have a neutrino experiment, we build our detector, we turn on the beam, and then if we see something unexpected in our detectors, we want to minimize the possible causes, and flux could be one of them, right? So pretty much every experiment I've ever worked on, you turn on your detectors and typically you see something weird, and it takes a while to understand what it is. And when you look, trying to figure out what it is, you have a long list of things that you have to check off. And, it'd be nice to make that list as small as possible. And if you have a large uncertainty on your flux, that means it's not so easy to rule it out. So we rely very heavily on a priori flux predictions. These are based on simulations of all of the complicated components, right, that I showed earlier, the target, the horn, the decay pipe, everything. So now I want to talk about the role of simulation. So again, this is a picture of what happens in this case. This is the NUMMI beam, but this is generically true for most accelerator-based beams. Coming in from the left, you have a proton, a high-energy proton hitting in this case, a segmented target. The proton interacts and creates other particles, pions, kaons, other protons. Those then go on, some of them escape, some of them go on and interact and produce more particles. And so you can have secondary or you can have tertiary interactions in your target. Eventually the pions escape, and then they go through and are focused by the horns. And then you have a collimated, somewhat more collimated beam entering your decay pipe. And then they eventually decay in the decay pipe into muons and neutrinos. These are the pions. And then the muons are absorbed in rock, and then the neutrinos go on. So simulations use the production cross-sections for protons, pions, kaons, all of these particles hitting a broad range of nuclear targets across a broad range of energies. For example, particles of all energies up to the beam energy interact in the production target. And maybe that's carbon or beryllium. But they also interact in the focusing horns, which are made of aluminum, and lots of other material. If I mentioned, we sometimes cool things with water, so maybe there's interactions in the water. There's titanium, there's iron, there's helium, there's rock, etc. Right? So we have to simulate all of these interactions, right? So a very broad range of nuclear targets and particles and particle energies. And we have to simulate all of this, right? So and then we also need the very detailed descriptions of the target and the focusing horn geometry and the focusing magnetic field as a function of position and time. So with all that said, there are two sources of uncertainties in these predictions, right, that we simulate. One is with hadron production, which sometimes people refer to as HP, and then beam focusing. Currently, hadron production uncertainties are the dominant uncertainty when it comes to the flux, right? And that's shown in the plot here, where it shows a picture for Dune, where the blue curve is the uncertainty coming from hadron production, which can be at very low energies as large as 16%. And then but the best is about 7 or 8%. And then there are other things like the focusing uncertainties related to the focusing, and that's shown in the kind of the orange brown, right? So where the peak is that dashed red line. That's where the oscillation peak is, and so there hadron production is the dominant uncertainty. All right, so in order to kind of get the uncertainties that we have, but also hopefully reduce them even further, we make in accelerator beams, we make a bunch of in situ constraints. Okay, so first of all, we have to monitor the primary beam coming in. That is, these are the protons coming in and hitting our target. And so we have to know exactly where the protons hit the target. And so there are many different detector technologies to do this. Remember, we have a very, very intense source of protons, right? It's a very high current. And so we need detectors that can survive that kind of environment. So to know the position of the beam on the target, both JParc and Fermilab use something called segmented secondary emission monitor, or SSEM. These are detectors where secondary electrons are emitted from a segmented cathode plane when struck by a primary proton, and then those are collected on anode planes, and those planes are 5-micron titanium foils. Then that creates a current, and so the cathode current is read out, digitized, and recorded to extract a beam profile. At JParc, they have something else called the optical transition radiation monitor, or the OTR. And so the OTR, this radiation, this optical transition radiation, is produced when charged particles travel between two materials with different dielectric constants. And so what you end up with is an image of the backward light captured by a rad-hard camera in a low rad area. So it's kind of off to the side a bit. And then in NUMI, to get the position of the beam, like right in front of the target, NUMI and LBNF will have something similar as well, is the target position thermometer, the TPT. So this is used, again, used at NUMI, and this is where proton beam heats up. So the protons, it's so intense, it heats up thin beryllium horizontal and vertical wires. And then these wires are connected to thermocouples. And so we can measure the position on these wires of the beam. And in fact, we can get a position resolution of better than 100 microns, right? 0.1 millimeters. So we can get the position and the stability of the beam to within that, which is, pretty amazing. Now we also use other devices. Wire secondary emission monitor, WSEM. This is done at JParc. And there they use twined 25-micron titanium wires. It uses less material than foil-based detectors, right? These are extremely thin wires, thinner than typical human hair. These are C-shaped. The C-shape allows the monitor to be moved in and out of the beam during beam operations, right? So it moves in and out like this. This device, though, was developed in collaboration with Fermilab, right? So this is something that JParc uses, but we worked on this together. And then there's the beam-induced fluorescence monitor, or the BIF. Where the way this works is that you locally degrade the vacuum level. So you inject some gas, and then when particles go through, it creates fluorescence from the de-excitation of gas molecules excited by the protons passing through. What's nice is that this is not destructive and can be used to continuously monitor the beam. Excuse me. And then there's the optical beam loss monitor, which is used to record where we lose beam along the beam line. So beam-induced signal on an optical fiber running alongside the beam from lost beam particles. What's nice here is that you can use precise timing information to localize the point of beam loss. So you can actually find where in the very long beam line that we have, where are we losing particles. And few of these channels are actually needed to monitor the entire beam line. So that's pretty nice. Sorry. So this shows some data from these detectors. And so these are kind of newer detectors from what have been used to date. And so the WSEM has the same resolution as the SSEMs. but it creates less than 10 times the beam loss of the older detectors. And they've been using these at JPark since 2018. The beam-induced fluorescence monitor, there's a prototype that was successfully tested in 2020 and 2021. And they're upgrading the system with a two-stage microchannel plate detector to increase the gain by about a factor of 10 to the 3. And they're also studying system with MPPC and fibers. And then the OBLM was installed in 2021 and it covers 91 meters of beamline with only 3 channels. So the plot above shows the mapping of the OBLM timing to different points along the beamline. Right? So those are working very well. Now, once you inject the protons onto the target, you then have to basically worry about making sure that your target and your horn are aligned, exactly where you want them to be, right? The far detector is very far, sometimes, order something like 1,000 kilometers or hundreds of kilometers away. So you want to make sure that you're aiming your beam in the right direction, right? And so the targets and the horn positions are determined via a beam scan across known features and measuring the scattering rate with different detectors. And so there's, in NUMMI, there's the so-called hadron monitor. It's not really a monitor, it's mostly used for alignment, but it's located at the end of the decay pipe. And then we also use beam loss monitors to track where the beam is. And so the photo on the left, these are examples of the hadron monitor, which is a pixelated detector. And basically what we do is we scan the beam. So on the bottom right, you can see the beam coming in, the normal beam in green. And then there are features for where the target and the horn are, like upstream. There's something called a baffle, which is a bunch of graphite, and then a bafflet, and then a target core. And so we kind of sweep the beam across these features, and we can see the beam scattering off of all of these features. So the baffle is there to protect the target utilities in the horn from missteered beam. What if it goes off by accident? And the bafflet protects the decay pipe windows and the absorber. And we also use a bafflet for alignment as well. So, and then we have other things like very thin wires in our horns that we use for horizontal or vertical alignment. So when the beam goes through, and the beam will scatter off of these wires, and then you can detect the scatter pattern, the scattered particles off to the side, and you'll see a large rate of those particles when you're hitting hitting those wires, so you know that you're hitting the wire. So here's some data as we scan the beam across. You can see the features here of the baffle and the target, and so you can now know exactly where the beam is relative to your upstream monitoring. Okay, muon and neutrino monitoring. So once you have once the pions have decayed in the decay pipe, they produce muons, and a lot of those muons are absorbed, but we allow some of them to pass through into muon monitors where we can measure the beam profile and detect any changes. So it's very important that we have a stable beam and that the things are not moving around a lot. Otherwise, that would significantly increase our flux uncertainty. And so so we have ionization chambers used at both JPark and Fermilab to monitor the muon beam. JPark also has an array of silicon pin photodiodes to measure the muon beam profile. JPark uses the INGRID on-axis neutrino detector to monitor the muon beam profile. Unfortunately, in NUMMI, we currently have no on-axis neutrino beam monitor at NUMMI, but for LBNF and for DUNE, we will have an on-axis monitor. And so you can see the ionization chamber pixels in the photo on the bottom left. These are the muon monitors, and we can measure the beam profile of both X and Y with these detectors. And then finally, the last in situ constraint that we have is, as I mentioned earlier, is neutrino electron scattering. So this is where a neutrino comes in, it scatters off of an electron, and this is, if it's a muon neutrino, then the way it interacts is through the neutral current interaction. If it's an electron neutrino, it will interact through either the neutral current or the charge current interaction. So this is a purely leptonic process, and so the theoretical uncertainty on this is on the order of about 1%. The signature is a very forward-going electron, only in the final state. And in principle, a measure of the electron angle gives a measure of the neutrino energy. So the equation above, it says 1 minus cosine theta E, that's the direction of the electron with respect to the incoming neutrino. If we can measure that, then there's a Y term in there, and that Y term is related to the neutrino energy. And so you can solve for Y and get the neutrino energy. Now, that sounds nice, but you need a very, very capable detector to do this. You need extremely good angular resolution. Even with liquid argon detectors, kind of the resolution, the angular resolution that we expect to get is kind of on par with the spread of neutrino angles coming into the detector. But a more capable detector in the future might, in principle, be able to measure this. Now, again, as I mentioned earlier, the cross-section is really tiny. It's about 1/1000th that of the charge current cross-section, but it does provide a constraint on the total flux. And what that means is that all neutrinos, right? So all neutrinos in all flavors, because things occur through the neutral current interaction. That means the antineutrinos will also give you the same signature. So the plot on the top right shows that this cross section is a function of neutrino energy, above kind of like 1 GeV, it's effectively linear as a function of neutrino energy. Now Minerva has used this to reduce their flux uncertainty normalization from about 10% down to about 3.5%. NOVA is working on an analysis of this now and might get to something like 5 or 6%, and DUNE expects to achieve about 2%. Okay, so those are all in situ constraints that we can use to both monitor and ensure the stability of our beam, as well as to reduce the uncertainty on the flux itself. Now I want to talk about ex situ measurements. So as I mentioned earlier, hadron production uncertainties are the largest uncertainty when it comes to the flux. And that's because if you look here, so what we have here are the fractional uncertainty of the flux as a function of the neutrino energy, broken down by the type of hadron interaction that produces the parent pion or kaon or other interaction that eventually resulted in the neutrino that went through the detector. Okay, and so there are rather large uncertainties on things that have never been measured, right? So if they haven't been measured, we kind of have to guesstimate what the uncertainty is. And so we put a 40% uncertainty on all of the interactions in the target and horns that have never been measured, or maybe they've been measured a few different times, but there's a large spread in the measurements. So the story is the same for both muon energy and electron energy. And effectively, it comes down to just simply there's a lack of proton and pion scattering data at lower beam energies. So a reduction of flux uncertainties will improve the physics reach beyond, or sorry, the physics reach of most of the near detector analyses, for example, the cross sections and the BSM searches, and any non-three flavor PMNS oscillation analysis. And then, of course, we want to support the oscillation program by increasing confidence in the a priori flux predictions and near detector measurements. All right, so can we do better, right? So if we look at these plots, right, you look at some of these, there are some rather significant uncertainties coming from nucleon interactions on different target materials. That's the light blue curve. And then meson incident, meaning pion and kaon interactions on different materials. And then just a whole bunch of other sources, but those are the dominant ones. So can we do better? So what we do here is we do a study where we assume that we're not going to make any further improvement on pion production where measurements at the level of 5% already exist. You know, those are very good measurements. But we're going to reduce the uncertainties for a lot of the other channels, right? So we're going to reduce the uncertainty for kaon absorption. And we're going to reduce the uncertainty by about a factor of 4 on quasi-elastic interactions, as well as on proton, pion, kaon hitting nuclear targets, and resulting in protons, and then a factor of 2 improvement for kaon production. Right, so if you look at the before and after, if we simply just, getting a 10% measurement is not particularly difficult, but these are all things that are not covered by data, right? So on the left is our current status right now with the uncertainties we have, and if we make some very modest measurements, we improve the flux uncertainty by about a factor of 2. And that's for muon neutrinos, and it's the same story for electron neutrinos. But it's not just about reducing uncertainties, right? So a lot of the cross sections that are used in the simulations for the flux are kind of estimating or guesstimating what the cross sections are, kind of interpolating or extrapolating from measurements. And so there's really no really good constraint on those. And so it's more about having a more robust flux prediction based on external data. Okay, so there are several experiments around the world trying to collect new hadron scattering and hadron production measurements. There's the Na61 SHINE experiment at CERN. You can see the person, there's a person, I don't know, kind of almost halfway along the line, the length of the spectrometer, right? This is an enormous spectrometer, many meters long, 13 meters long. This is a very high acceptance spectrometer with DEDX and time of flight measurements to identify particles. It's designed for beam momenta greater than 20 GeV, but they are hoping to rearrange their beamline in order to collect data for momenta below 15 GeV. This is an experiment that's been running for over 15 years. They've also made measurements using actual long neutrino targets. Then there's Emphatic at Fermilab, which uses the Fermilab test beam facility. This is kind of on the opposite end of things. This is a very small experiment. It's tabletop. The idea is to collect data at lower beam momenta where most of our uncertainties are coming in. At the FTBF at Fermilab, you can get beams all the way up to 120 GeV, so that they'll also make measurements at higher momenta. So the ultimate design is a 350 milliradian acceptance spectrometer, but it's compact and that reduces the overall cost. It uses a high rate DAQ and precision tracking and timing. And it's an international collaboration focused solely on measurements that will improve neutrino flux predictions with all of the appropriate stakeholders from NOVA, DUNE, So basically all of the Fermilab experiments, but also the Japanese experiments, super K, T to K, and hyper K. All right, so now I want to talk about future prospects. The experiments that I mentioned have taken mostly thin target data. So these are just pure cross sections. And these are extremely useful and generally necessary for improved flux predictions. They're also needed for improved flux predictions for atmospheric neutrinos. And they're also just generally helpful to the HEP and nuclear community. Now, measurements by the MIP experiment, which ran about 20 years ago, and NA61, these two experiments took data using real or replica neutrino production targets, these complicated targets that I showed earlier. And those we've demonstrated that we can reduce the hadron production uncertainties by nearly a factor of 2 by taking data with these thick targets, these replica targets or actual targets. So NA61 SHINE has collected data using a replica NOVA era NUMI target and plans to, well, they've also done the same thing for the T decay target. And in fact, the plot on the bottom shows what happens when they use the replica target, which is the solid black line, versus using just a whole bunch of thin target data that they collected. And you can see that the uncertainty goes down by about a factor of 2 in that case. And then on the top, for the using the data from MIP, also had a much improved, not quite a factor of 2, but more like maybe a 30% reduction in the uncertainties, the hadron production uncertainties. And so NA61 has collected more data with the NOVA NUMI target. And then within the next, I believe it's this next year, they're going to be collecting data using a prototype LBNF target. And then they're also, as I mentioned earlier, considering collecting data at lower beam momenta in a couple of years. Now, Emphatic is also getting ready for its phase 2, where because this is the tabletop, the idea is to actually literally put it on a table, in this case, a motion table, and to collect data for the first time downstream of both not just a target, but a target and a horn. So you can actually see what eventually comes out of the horn and what these are the particles that enter your decay pipe. So the minimal goal here, the idea is to put the detector on a motion table downstream of a target and a horn. The minimal goal is to measure the charged particle spectrum downstream of the target and horn. A power supply is also available. In phase 2, we will not be powering the horn, so that the particles will not be undergoing focusing. But the particles still have to go through the horn and the horn material. And so we hope to establish that this kind of measurement can be done, and to do this with a pulsed horn in the future. So this establishes a program to address questions not only of hadron production in the horns, but also of the modeling of the horn geometry and the magnetic field, right? So again, the horns are quite complicated. The magnetic fields are not really trivial. And so, it's always better to measure something than to rely on calculations. Okay, and then I'm running out of time, so I'm going to go rather quick, but there are also planned improvements for monitoring the beam and measuring the position, the stability of the beam. There are ideas of having an in situ detector that will constantly be measuring the hadron rate, which is a way to monitor the overall protons on target coming out of your target. And this is using an RF resonator by measuring gas permittivity which is proportional to the intensity of the charged particles passing through it. What's nice here is that the detector is rad hard, and they demonstrated that we could actually see the 6 main injector batch structure from the accelerator in the data that they collected. For LBNF, we plan to measure to monitor the horn positions. And so, in fact, in NUMI, we had an incident where a horn actually dropped about 3 millimeters. And this was during operations, and it took a long time for us to figure out what happened because we had no way to actually directly observe this, except that we observed that the neutrino spectrum changed. So we saw something change, but we didn't know what. And so here we want an independent measure of the height of all of the relevant beam components, especially the horns. And so this is a hydrostatic leveling system where you can measure very, very tiny changes, sub-millimeter changes of the level of water, which will happen if a horn tilts or drops. And so that's under development now. And so the measurement uncertainty is less than 5 microns. And we've already been testing the prototype for these, and things look very good for this. For muon monitoring, some other improvements for other detectors that are more rad hard, and also a current transformer. The nice thing about the current transformer is that it's sensitive to both neutrinos and antineutrinos because you have muons and negative muon, positive muons and negative muons. And as they go through the current transformer, the charge partly cancels out, and so you now have you can measure the overall rate by looking at all of the charged particles, but then you can get some sensitivity to the overall fraction of your wrong sign background, meaning there should be, if there's mostly muons, there is some small fraction of negative muons, and you want to measure that. And so this is an interesting idea. Okay, so I'm going to wrap it up because I'm out of time. So flux never just cancels in 2-detector neutrino oscillation experiments. Flux uncertainties are a limiting systematic on many single detector measurements and searches for BSM. The primary, secondary, and tertiary beams are all measured and monitored in real time and to provide in situ constraints on the beam. The ex situ measurements of hadron scattering and production of both thin and thick targets are critical to constraining the flux and the flux uncertainty. And finally, if we want to do better on the flux, then we need new hadron production data. And there are many experiments, or 2 experiments at least, that are trying to make new measurements that will be useful to the neutrino community. So that's what I have for today. And I'll stop there.
Thank you, John, for a nice overview on neutrino beams. Would you like to take some questions, 1 or 2?
Sure, happy to.
Yeah.
Yeah, so on slide 31, where you showed the relation between electrons scattering angle to reduce neutrino energy. So the angle theta is still the angle between the incident neutrino and the outgoing electron. And
That's
since
right.
we don't know the exact information about the neutrino, so there will be an uncertainty in the angle. So is that like negligible, or that still is a serious effect?
Yeah, no, very good question. So that depends on the experiment. The further, if you're doing this in the near detector, the further away you are from the neutrino source, right, then basically that means your neutrinos are coming straight in. And so, if you imagine you are, oh gosh, I don't know, a kilometer away from the neutrino source, and I don't know, the angle of the neutrinos is going to be pretty small compared to compared to that, right? So let's say your detector is, I don't know, 10 meters is actually huge. So let's call it 5 meters. That's actually pretty big, but 5 meters across. And you're, let's say you're a kilometer away, you're talking about kind of a 5 milliradian divergence, right? And so if you can measure, if you can measure better than that, you can model these things, right, and take that into account. But it is a limitation. So yes, you are absolutely correct. It is a limitation that we have to basically model. But yeah, but the further you move your near detector away, the smaller of an effect that becomes.
So as we explained in the slides, that for the vector flux measurement, we need to lower the cross-section uncertainties, right?
Yeah, which slide?
So to understand the flux in better way, we need to lower the cross-section uncertainties, right?
Well, so it's kind of a circular argument, right? So the problem is that the cross-section depends on the flux, right? The flux is basically the denominator of the cross-section, right? And so if there are no theoretical uncertainties on a cross-section, like for example, the neutrino electron scattering, then you can use this as a way to measure the flux, right? But this is a rare process. It takes a long time, right? And sometimes it will be years before you actually know the answer. So if there were other neutrino cross sections that had very small uncertainties, then we can do the same thing. But right now, as I'll talk about tomorrow, and maybe you've already talked about it a little bit, the cross-section uncertainties are kind of at the level of 20%. And so there's a lot more work that has to be done to improve cross-section uncertainties.
Okay.
On the theoretical side. Yeah.
So we normally use beryllium or graphite targets. As you have mentioned that there are some prerequisites for this to targets like thermal conductivity and melting point. Like only these two are capable of those prerequisites, or there is some special reason that we choose these targets?
Well, the reason we often use these is because yes, they have the right properties. There are some other materials out there that also have, I think, pretty good properties, but they tend to be just honestly a lot more expensive. And beryllium is not easy to deal with either. It's a very dangerous material to work with. But compared to other materials that would satisfy the requirements and that could handle the power and the heat, these are the easiest to manufacture, I think, and they're just not as expensive.
And another thing, you have said that there is some uncertainty related coming from the beam focusing thing, like focusing horns. You didn't elaborate there, so if you can comment on that.
Yeah, let me see. So here, no, here. So okay, so in this plot here, so the focusing uncertainty is shown here, right? Okay. Now, where does that uncertainty come from? Okay, you have these complicated horns, and so there are many ways that we could get the focusing wrong. So first of all, we put a current into this, right? And we have to know that current very well. Typically we know the current to within about 1%, maybe a little bit better than that. But if it goes much beyond that, then that will change the how much you focus or over focus, under focus, etc. Then there are things like the alignment of everything, right? So imagine these are like lenses, right? We often talk about in accelerator physics, we talk about beam optics, and so these are, you can think of them as lenses. And so if you have two lenses and they're slightly, off position, things will become a little bit defocused, right? And so if they are in the wrong position, either along the beam direction or transverse to the beam direction, these all can have effects on the pions that get focused or under focused or over focused, right? And that results in a change in the underlying neutrino energy spectrum. And so there's lots of different things that can, there's alignment, but then there's angles as well, right? These are all things that we build it, we have our specifications for how well we have to build it. And the uncertainties that we have come from how well we can build it effectively.
So these are more of a mechanical uncertainties in these things.
They're a bit of mechanical. I think there's also maybe there's other stuff like the electric field inside like the skin depth of the horns. There's some uncertainty in what the actual skin depth is. Even though we've gone and tried to measure it, the measurements are not perfect. And so the measurements themselves have uncertainties, right? So yeah, it's mostly mechanical, like knowing exactly where everything is, and once we install it, that it hasn't moved around. And so, we hope we can do better in the future. But yeah. All right, thank you.
Thank you.
Thank you.
Thanks.